In this class, we are going to discuss about numerical and circle diagram of the three-phase induction. A 15 kilowatt, 400 volts, 4 pole 50 hertz, three-phase star connected three-phase induction motor gave the following test results: no load test and block rotor test. During no load test, the line voltage is 400 volts, line current is 9 amperes. The power taken by the induction motor during the no load test 1310 watts. During block rotor test, the line voltage 200 volts, line current is 50 amperes. The power taken by the induction motor during the block rotor test 7100 watts. So one more point also given: the stator to rotor copper loss are equal at a standstill. Draw the induction motor circle diagram. Calculate line current and power factor, slip, torque, efficiency at a full load. Maximum possible power factor and corresponding line current. Maximum power output and maximum power input. Slip at a maximum torque occurs and maximum torque and starting torque. These are the parameters what you have to calculate after developing the circle diagram of three-phase induction motor. Now we are going to see one by one. From the no load test, you can find the no load power factor. The no load power factor cos pi naught equal to no load power divided by the root 3 VL IL. So 1310 by root 3 400 into 9, we are getting the 0.21. So the no load angle theta naught equal to 77.88 degrees. The no load current is given directly, that is 9 amperes. From the block rotor test, short circuit power factor, the short circuit power factor cos theta S equal to the power taken by the induction motor during the block rotor test divided by root 3 VL IL. Substitute all the values, you are getting the 0.41. Theta S equal to 65.80. Now we are going to find out the short circuit current at a rated voltage, that IS equal to 400 divided by 200 into 50. Because the 50 amperes of current is taken by the induction motor due to the block rotor, if you apply the 200 volts, how much current is taken by the induction motor if you apply the 400 volts? We are getting the 100 amps. Now we have to take the scale 6 amperes equal to 1 centimeter. This is the current scale. With the help of this scale, now we are converting this 9 amperes no load current 9 amperes into the centimeters. So 9 by 6 equal to 1.5 centimeters at an angle 77.8 degrees. So now we are going to draw the O dash with a length of 1.5 centimeters and angle with the vertical axis, nothing but a y axis, 77.88 degrees. The same manner, to convert this short circuit current 100 amperes into the centimeters. So 100 by 6 equal to, we are getting the 16.67 centimeters at angle of theta naught equal to 65.8 degrees. Now with the help of these two values and angles, now we are going to develop the circle diagram of a induction motor. Now we have to take the x-axis, the y-axis. Already we know the no load current, that is 1.5 centimeters. First you have to draw the, this is O dash, this is no load current, this length equal to 1.5 centimeters. From the vertical axis, this angle equal to 77.88 degrees. Now from the tip of the I naught, you have to draw one horizontal line parallel to the x-axis. Now this length is representing the fixed losses in a induction motor. Now you have to draw the short circuit current if you apply the rated voltage, that is nothing but a 16.67 centimeters at an angle of 65.8 degrees. Now from the vertical axis, you have to measure this angle 65.8 degrees. Length becomes a 16.67 centimeters. You draw a one vector. Now this angle is nothing but a 65.8 degrees. Now this length, red line length, becomes a 16.67 centimeters. This is nothing but a, this point is nothing but a O, this point is nothing but a, this is O dash. Now we combine the O dash and A, it gives the output line. Now bisect the O dash A, we are getting the center for the circle, that is the C. Now you take the C as a center, O dash C as a radius, and draw a circle. We are getting the one half circle which is touching this black line at a D. Now in the numerical itself, it is given the stator copper loss equal to rotor copper. So You have to draw one line from A perpendicular to the x-axis. AF you have to divide equally. You are getting the point E. From the point E, you combine the O dash, you are getting the torque line. So why we are dividing this length AF equally means the numerical it is given that the stator copper loss equal to the rotor copper. This line is nothing but a torque line. This is fixed losses. This is stator copper losses. This is rotor copper losses when the induction motor in a block rotor test. Now you have to find out the line current, power factor, slip and torque and efficiency of induction motor at full load. Full load means the rating of the induction motor is given. First of all, you have to calculate the power scale. Now the power scale equal to x into V1 watts, where V1 equal to 400 by root 3 because the stator winding is connected in a star. The voltage which is given in the numerical, that is the line voltage. So 400 by root 3. This is the phase voltage. X is nothing but a current scale. Already we have taken the current scale 6 amperes per centimeter. Now multiply these two, which gives the power scale that is 1358.7 watts per centimeter. Now we have to convert the full load power of induction motor into the centimeter. But what are the parameters we are drawing in the circle diagram? All those parameters are the per phase values. So the full load power per phase equal to 15,000 by 3, that gives the 5,000 watts. Now that we are converting this 5,000 watts into the centimeters by dividing this value in power scale, we are getting the 3.61 centimeters. This is nothing but a per phase rated power of induction motor in a centimeter. So from the tip of the A, we have to draw a one line whose length is equal to 3.61 centimeters. Now this take it as a B. Now you draw a one line from the tip of the B and parallel to the output line. That line is nothing but a black dotted line. That is intersecting the off circle at this point. This point you take it as a P. Now you combine the point P and O. That is nothing but a full load current taken by the induction motor. This angle is nothing but the angle between the voltage and full load current taken by the induction motor. So if you measure this angle, you are getting the 29.5 degrees. Cos of that angle is nothing but a 0.87 lakh. Measure the length OP, you are getting in centimeters. That centimeters you are converted into the amperes by means of a current scale. So we are getting 16 to 6.5. You're getting the 36.3 amperes. Nothing but this length you are getting, the OP length becomes a 6.5 centimeters. Now from the point P, you draw a one vertical line perpendicular to the x-axis. It is intersecting the output line and torque line Q, R, S, T. You can calculate the slip of the induction motor if you know the rotor copper loss and the rotor input. QR is nothing but a rotor copper loss. PR is nothing but a rotor input. So QR by PR equal to, if you measure this length, you are getting the 0.25 centimeters divided by P. You measure the length PR, you are getting the 3.85. You are getting the finally 0.065 is the slip of the induction motor at a full load. Next, full load torque. If we know the rotor input power, the rotor input power equal to the length PR. So length PR into power scale into 3, because this value you are getting the per phase value, so we want the 3 phase. Again you have to multiply with this value with the 3, divide by omega s. You can calculate the synchronous speed of induction motor because it is a frequency 50 hertz and number of poles for which the motor is designed for the 4 poles. The synchronous speed we are getting 1500 rpm. That we converted into the omega s value 2 pi ns by 60. You are getting the 50 pi. So 1 by 50 pi into 3.85 into power scale into 3, you are getting the 101.89 Newton meter. Next, efficiency at a full load of induction motor. Here in this diagram, the output power is nothing but a PQ. The total power taken by the induction motor at a full load, that is equal to PT. So the length PQ divided by the PT is nothing but a efficiency of induction motor. You're getting the 0.809 into 100. You're getting the 80.9%. So in this manner, you can calculate the line current and power factors before the induction motor and torque. Second parameter is the What is the maximum current taken with induction motor and what is the possible maximum power factor? To find the maximum possible power factor from O, you have to draw a one line which is tangent to the intersecting. This line where intersecting the circle, that point you take it as P. Now, the length OP is nothing but a maximum current taken by the induction motor. The angle between the OP and V, the cos of that angle is nothing but a maximum power factor. So once we got the length OP by means of a current scale that we have converted into the amperes, you're getting the 36.3 amperes. You measure this angle, cos of that angle, you are getting the 0.87 lakh. Maximum power output. To find the maximum power output, from the point C, you have to draw a one perpendicular to the output line that is intersecting the circle at a U. From the U, you draw a one vertical line perpendicular to the x-axis that we represented with a dotted line. Now you take this point, that is U dash, where this dotted line is intersecting the output line, that is the U dash. Now the maximum power equal to 3 into length U dash into power scale gives the maximum power developed in a induction motor. So we are getting this length, we are getting the 5.3 into power scale into 3, we are getting the 22.03 kilowatts. To find the maximum input, again from the point C, you draw a one line perpendicular to the x-axis that is intersecting the circle at this point. That point you take it as a V. Now, maximum input power taken by the induction motor, that is equal to, you measure this length. After measuring this length, that you have to convert it to watts by means of a power scale. So 3 into power scale into length VC plus fixed losses, nothing but this length FG. Substitute all the values, you are getting the 3 into this length, you are getting the 8.45 centimeters into power scale plus already we calculated the fixed losses that you have to take here. Finally, you are getting the 36.497 kilowatts. Maximum torque development induction. From the point C, perpendicular to the torque line, you draw a one line that is intersecting the circle at a one point, that is W. From the W, you have to draw a one line perpendicular to the x-axis that we represented with the dotted line. So the length W dash is nothing but a rotor input at a maximum torque. So 3 by omega S W dash into power scale, substitute all the values, we are getting the 176 Newton meter. Next is slip at a maximum torque. Again, to find the slip at a maximum torque, we should know the rotor copper loss and the rotor input. XW dash is a rotor copper loss. WW dash is the rotor input to the induction motor at a maximum torque. Now take the ratio between XW by WW dash. Measure these two lengths, 1.58 by 6.65. We are getting the 0.238. Next, we have to calculate the starting torque. See, this line is representing the AG is representing the power taken by the induction motor at the time of starting. Nothing but a block rotor test data. This is nothing but a rotor copper loss. This length is nothing but a rotor input. So when you're going to find out the starting torque, this length that you are converted to power. So 3 by omega S into length AE into power scale, substitute all the values, getting the 87.3 Newton meter. So in this manner, we can calculate the different performance parameters of a three-phase induction motor by developing a circle diagram. So thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of my YouTube channel, so that I am always welcome to answer all your questions.